Hello and welcome to non-IITian. In this video, we are going to talk about a problem in linear algebra from NBHM 2025. If you're enjoying the content, please don't forget to like, share, and subscribe to non-IITian. So let us quickly understand the statement of the problem first. So let A be an n cross n matrix with real entries and having rank 1 where n is greater than or equals to 2, find determinant of A plus I. I is the n cross n identity matrix. Okay. In terms of A, that is important. I need to find it in terms of A. Okay. In terms of A, in the sense, in terms of properties of matrices related to A. Okay. Fine. Let's start with the problem. So what are the things given to us? So we are given that A is a n cross n matrix in R, okay, with real entries such that rank of A is 1. That's exactly what is the most important thing given to us. Okay, what do you mean by rank of A being 1? Okay, let us quickly recall something. Suppose lambda is an eigenvalue of A. Suppose lambda is an eigenvalue of A, then recall that the geometric multiplicity, okay, let me write it for the first time in full form, then the geometric multiplicity of lambda, which we generally write it as gm lambda of A, is given by the nullity of the matrix A minus lambda I. Okay, and the nullity is basically the dimension of the null space of A minus lambda I, which is also called the eigenspace of the eigenvalue lambda. Okay, so now observe that since rank of A is equal to 1, which is obviously less than n, where n is the dimension of A, because it is given that n is greater than or equal to 2. So this implies that the determinant of A is 0. What does this imply? This implies that 0 is an eigenvalue. Right? 0 is an eigenvalue. Now what is the geometric multiplicity of 0 in A? So this is the nullity of A minus 0 times I, which is nothing but the nullity of A. But then by the rank nullity dimension theorem, we know that this is nothing but the dimension of A. But what do we mean by the dimension of A? I'm just focusing on that for a minute. Minus rank of A. And by the dimension of A, what I typically mean is the following. Recall that when given A is an n cross n matrix, this is nothing but linear transformation from Rn to Rn. So dimension of A is basically the dimension of the domain vector space. Okay, so this is just, I'm trying to write it as n. So this is n minus 1. So what have we concluded from here? Therefore, the geometric multiplicity of lambda is equal to 0 is n minus 1. Also recall what is the algebraic multiplicity of an eigenvalue? The algebraic multiplicity of lambda, this is always greater than or equal to the geometric multiplicity of lambda, right? If the algebraic multiplicity equals the geometric multiplicity, then the matrix becomes diagonalizable, something which we should know, because then you can form an eigen basis with respect to that eigenvalue. Okay, this must hold for every eigenvalue. I should have mentioned that. Okay, nevertheless, we do not require that here. So therefore, the algebraic multiplicity of lambda is equal to 0 must be greater than or equal to n minus 1. Okay, so what do we conclude from here? Therefore, the algebraic multiplicity of lambda is equal to 0 is either n minus 1 or it's n. Right? Because the dimension itself is n, so it can at most be n, and it can at least be n minus 1. Okay, so this is what we actually require, and now we'll see that we are actually done. Okay, now so what I want to say is that now suppose lambda is the other eigenvalue. There can only be one other eigenvalue except 0, right? because 0 occupies at least n minus 1 of the places of in the eigen in the eigen spectrum. So now suppose is the other eigenvalue. Then what we know, then the sum of all the eigenvalues equals the trace of A. So then lambda plus 0 and so on, right? So these are n minus 1 times, okay, because we know that at least it's n minus 1, so I should have this. So this must equal the trace of A. Hence lambda is nothing but the trace of A. Is it clear? But then what can I have? But then this implies that, so therefore my A has the eigenvalues trace of A and all the other being 0, which we are sure of. Trace of A can also be 0, we are not concerned about that, but at least it's trace of A. That's exactly what I want, right? Now comes the funniest part of the problem. We know that every matrix need not be diagonalizable, but it's triangulable, right? So since A is triangulable, this implies I can have A similar to a matrix which is of this form, right? Every other entry is 0, right? So it should be of the form some, we know that it should be of the form some P times this P inverse. So therefore my A plus I, this should be of the form P times this matrix into P inverse plus I can be written as P times P inverse. So this is P times trace of A plus 1, and so this is 0 plus 1 and so on till 0 plus 1 times P inverse. And I hope we are done now, right? Therefore my A plus I has eigenvalues of the form trace of A plus 1 and all the rest being 1. So therefore the determinant of A plus I, which should be product of lambda belongs to the spectrum of A as eigenvalues, so this should be equal to trace of A plus 1 times 1 times 1 and so on, which is nothing but trace of A plus 1. And that's exactly the answer for your problem. Is it clear? Thank you for watching. Please like, share and subscribe to Non-IIT, and if you like the video. Meet you guys soon.